High-power lensless THz imaging of hidden objects. THz time domain spectroscopy offers the advantage of highly sensitive field resolve detection. We use high-power ultrafast laser to generate THz with milliwatt of average power. Our 100-watt class laser gets split into two parts. 99% of the power is used to directly drive THz generation. Folding mirrors extend the path lengths that a later time overlap between pump and probe pulse can be found. For efficient THz generation, the pulse front of the near-infrared laser should be tilted with a transmission grating. An spherical lens images the beam from the grating into a trapezoid lithium niobate crystal. The generated THz beam is emitted perpendicularly to the front surface of the trapezoid. To sample the THz pulse, 1% of the total laser power is used for the probe arm. After passing through a fast shaking delay stage, the beam propagates towards a retroreflector placed on top of a motorized linear stage and is finally coupled into a fiber. On the other end of the fiber is the photoconductive antenna, which can now detect the THz radiation. A 3D printed mixed polymer sample with low THz reflectivity is placed on top of a rotation stage. The sample gets covered only by a fraction of the highly diverging THz beam emitted by the crystal. The great advantage of the lensless imaging technique is that no a priori information about the position, orientation, and shape of the sample is necessary. The reflected THz signal has a large amount of information from the sample since THz time domain spectroscopy measures the full electric field. We image the same object with a common commercial system and or high-power setup using the same number of the average THz traces, the same integration time, and the same antenna configuration. The figures demonstrate the enhanced imaging capabilities of our high-power system on the left side. The contour of the target is clearly reconstructed, where in the case of a commercial system, the target is lost in the noise level. We also demonstrate lensless imaging through a wall with the test object concealed in a wooden box using our high average power THz source and increasing the detection exposure time. The shape of the object is retrieved with a clear contour and the size of it is perfectly matched with the measured edge lengths. These results promise to unleash the full potential of lensless imaging driven by a high-power THz source, especially the lensless imaging of concealed objects in real-life scenarios, which was so far impossible to realize due to constraints in the signal-to-noise ratio.